Hi, this is Don Allen, and in this short lecture we're looking at spider plots from iterations. Remember, our continuing goal in this chapter is to determine numerical solutions to the nonlinear equation f of x equals 0. As we've seen, most iterative methods begin by converting this equation to one having the form x equals g of x, where it is assumed that both of these equations have exactly the same solution set, meaning if we can find the solution of one equation, we will have a solution to the other equation. We'll assume g is differentiable over an open interval containing the solution we seek, although a Lipschitz type condition is possible and makes this also valid. However, then beginning with an initial value x0, we define iterates x sub n plus 1 equals g sub xn for n equals 0, 1, 2, 3, and so on. It's easy to see that we can look at two sets of these iterates and take their difference, and this will give us x sub n plus 1 is equal to minus x sub n is equal to g of x sub n minus g of x sub n minus 1. By the mean value theorem, there is a value c in the interval defined by x sub n minus 1 and x sub n, such that the absolute value of x sub n plus 1 minus x sub n in magnitude is equal to the magnitude of g of x sub n minus g of x sub n minus 1, and that is equal to the absolute value of the derivative of g at some point c, at the point c, times the absolute value of x sub n minus x sub n minus 1. So if the magnitude of the derivative is less than 1, the iterates will converge, as we've seen from the text. There are any number of ways to make this conversion, but the key is to get one where the derivative, g prime, is smaller than 1 over an open interval containing the solution we seek. We will demonstrate the convergence using what is usually called a spider plot, and what I have is one of them. We are seeking a solution of x equals g of x. G of x is going to be in blue, and x is this straight line here, and we're looking at the square from 0 to 3 on both the x and y axes. Our initial value is going to be 3, and so we evaluate the function at 3, come over to x, and that's going to be x sub 1. X sub 0 is 3, x sub 1 is this value here, and then we compute the value of the function at that point and swing over to x again, because that gives us what we're going to compute g at next, and there's the value g. See, we don't have to go all the way down to the line here. And then we repeat the process, evaluate the function there, and swing over to the line y equals x, and go up to the function again, evaluate and get the function value, go to x, get the function value, go to x, get the function value, go to x, get the function value, and so on. And this zooms in on the solution, and the solution is where the blue function, which is the function g, intersects with the function y equals x. So that's a typical spider plot, and what we're going to do is look at the actual generation of these spider plots for a couple of different functions. Hi everyone, in this part of the video we're actually going to make some spider plots using Maple. For this we need the function. Recall we're solving x equals g of x. We need a starting value, x0, and the number of iterations we're going to take. And we begin with the Maple Maple code, and that is to include the plots package, which we'll be using. So that's neither here nor there. What we're doing is looking at the mathematics, and we're going to look at the same function that we've looked at before, 2.2 minus 1.2 times the square root of x. And the blue part is the output from Maple. The red part is the input to Maple. You notice I put the thickness as 2, so it's a little thicker line than you would get normally. All right, so that's the scenario. We're taking x naught to be 3. So let me add that in there. And let's now begin the computation. And now we have to compute all the links in the spider web this way and plot it all out. And so you can see we have done it exactly. We started at the point 3. We swung over here to the function value at 3 and then evaluated the function at that value, whatever it is. We can certainly check it. And then we swing over to the value x. See, the x on the y is the same as the x on the x because it's we're right on the line y equals x. Evaluate the function there. Swing over to that particular value of x, compute the value, and so on. We zero in to the 0 of the equation, and as you can see, it does come in right to where the intersection of the line y equals x and the function g of x intersect, which is exactly the solution that we're looking at. All right, in the next part we're going to look at another function, so hang tight, here we go. Okay, now we're going to look at the function g equals 1 plus cosine x and see how it works in this particular case. We'll keep the same n equals 20, and this time we're going to start at point 2, and we plot the whole affair, and this is what we'll see. Once again, you can see that the slope is not as small at the intersection point. In fact, the slope is almost equal to 1. It's slightly less than 1 at the intersection point. Let's see how that affects the iterates. So we compute them, and then we print them out. So now you can see that starting at point 2 down here, we go up to the function value, swing across, and then compute the function value, swing across to y equals x, and compute the function value, and so on. And around and around and around we go. And after 20 iterations, we're not even close. So you can see this one is converging much slower. I think maybe what we should do is jump up the number of iterations. Let's go up to 100. The number of iterations is way up here. 100. So let's look at it again. Compute and compute. Now you can see even after 100 iterations, we're still not at the root, but the plot is becoming so dense it looks like a solid line. And that's what happens when the derivative is almost 1. The convergence is very slow. If you recall from the inequality, it is desirable to have the derivative much smaller than 1. That will affect the convergence. So now let's look at one which actually diverges. Okay, we're going to look at the function g equals 1/3 times the exponential function of x. We have the iteration set at 100. Let's go back to 20. Let's start again at point 2 and see what the whole thing looks like. All right, in this particular one, you can see there are 2 solutions to the problem. Now, it is possible to confuse the methods, and it can't find either one. It keeps bouncing around. But in this case, we're going to start at point 2, which is way over here, where in this region here, the slope is actually less than 1. In this region here, at the second root, the slope is greater than 1. So let's do the computation, and then the plot, and you see that the spider plot is coming in. It looks like sort of a staircase, but it is going right to that solution right there. Alright, now let's see what happens when we go to the other point where the derivative is larger than 1. And that value looks to be about 1.5. So it's not exactly 1.5, but we're going to start it right at 1.5, which means we're almost on top of the root. Let's take a look. There's the same plot. And now we print it out, and what you can see is that the thing is converging, or seems to be converging, down to this point. So what we're going to do is continue the solution and take a greater number of points, say this time 100. And now it has started here, and it has tracked downward and found the first root again. So now let's go on the other side of 1.5. See, there's a lot of data computed here. Let's go to 1.65 and start it off there. Same picture. Now plot it out, and now what you see, we've started on this upswing here, and we go, it is going away, so it's diverging. And that's the idea of these spider plots. And we'll stop right there.